Hello guys. Um, Hello guys. Hello everyone. Thank you very much for joining this section. And we are going to tackle AC theory in this meeting. Stay glued to your seat and please follow closely as I take you through alternating current theory. So from the beginning of applied electricity, we've been doing direct current, which we call DC. Okay, DC for short, direct current, meaning that the current is what direct. So most circuits you realize they give you resistor in series with another resistor, then maybe connected to a voltage source, right? Then current flows from the positive side in that direct manner throughout the circuit. Okay, so that is direct current. Now we are going to talk about alternating current. So first of all, when you say something is alternating, meaning that it goes up, comes down, goes up, comes down, meaning that it is trying to change value or change form within two different possible domains. Or when you say something is alternating, meaning it is switching forms, right? So it goes up, then it comes down, it goes up, and it comes down again. So that is the concept of alternating current, which we're going to illustrate in this tutorial. So now, there are some elements we are going to see in alternating currents. There are some, sorry, we are going to see in AC circuits, okay? Then there are some elements you also saw in the DC circuits. Realize that in the DC circuit, you made use of mostly resistors, then our power sources, which is voltage source, which, and you also have a current source, right? Then mostly voltage sources. Now, in the AC circuit, there is something different here, okay? So in AC circuit, represent it with a dwindle sign indicating AC source. Okay, it's a dwindle, meaning it keeps on changing. Now in AC, we make use of capacitors, we make use of inductors, as well as resistors itself. Okay, so we are going to be introduced to different elements in the circuit whenever you are doing AC theory, and because most students are not familiar with it, they find it quite difficult. So in this tutorial, I'm going to take you through step by step what alternating current is, how we go by these capacitors, inductors, as well as resistors. Now, let me give you some short practical explanation of AC. Now, let's say you have a naked wire, right? If you have a naked wire and a person touches it, if that wire is carrying a DC or direct current, then that wire, if a person touches that wire, you become part of the circuit. So assuming that you are having a circuit, okay, you're having a circuit and you have a voltage source, right? So when this voltage, right, produces current, the current is going to flow and passes, it will pass through this resistor, okay, then it will come, then since it's the direct current, it's moving directly through its path, right? So if it happens that you touch this side, your hand will also form part of the circuit. So let's say you have somebody standing here, right? You standing here like this, and your hand touches this part. Okay, you yourself will form part of the circuit, and the circuit will connect this way. So meaning that this circuit will, the current will continually pass through you. Then you will step, right? That's what we call electrocution. So for a DC source, whenever there is electrocution, you are not released. You cannot even release your hand because you become stiff and you die instantly. Then let's say you're having AC source. So in the situation of an AC source, let's see what happens. In an AC source, you the same person you are here, you touch this part of our source here, right? So let's say I have a resistor here like this. Now, whenever you touch an AC source, what happens is the current will first pass through you, okay? It will pass through you, so it will move, it will pass through you, then after it returns to zero. That is why AC is represented by a sinusoidal wave. It achieves its peak value, then returns back to zero, then also comes again in the negative side, then come back. So it keeps on alternating. So this side and this side keeps on alternating, right? So whenever AC current passes through a person, right, what happens is at this section, the current will pass through you until the peak is achieved. So you'll be in touch with the circuit, but once it reaches zero, you get released. That's why whenever you touch, let's say, a wire with an iron, or maybe even our outlets, power outlets in our homes, realize that once you get electrocuted, you just release your hand. You release your hand because in an alternating current, once the voltage or the current reaches zero, you are able to release your hand. But for the same situation with DC, you cannot release your hand because there is no instance that the value of the current will go zero because it's constantly flowing, right? So DC sources which are higher are very dangerous, and we are advised not to play with it. Unlike the AC where you can release at a point, right? Now that was just a brief overview. So now let's see something here. So what is alternating current? As I said, it's a current that keeps on alternating. So it follows a sinusoidal wave, and that is the ideal representation of AC circuits all the time. Now, in every AC, what happens is we achieve a peak value here, okay, Vm. If it's a voltage, we achieve a peak voltage. Then if it's a current, we achieve a peak current, right? If it's a current, we achieve a peak current I. Now, what does this peak mean? This peak means that in an AC, the change in current or the change in voltage occurs from zero. So it starts from zero, increases little by little until a point where it doesn't increase further. Then it comes down to zero, then comes back to the negative side. Okay, then goes back like that. Now, if we want to analyze AC circuits because of this changing nature of AC, how do we then define our voltage at any instance? If I want to find the voltage or the current in any part of an AC circuit, how then do I find my voltage, right? Meaning that we need to have a particular value that will represent all this change in our voltage or current as we have here, right? So that is where we come up with two different parameters, where the first one is called the average value. Okay, we have the average value, or we see the DC value. Then the second is what we call the root mean square value. Okay, the root mean square value. In short, we say RMS value. So these are the two values we determine from an AC circuit in order for us to analyze it efficiently. Okay, now having known this, let me take you through what happens when a DC current passes through a capacitor. So as I told you, whenever you're going to talk about AC, we deal with capacitors and we deal with what? Inductors, right? So now let's see, you've already had experience with currents passing through resistors and you are familiar with that. Now what about currents passing through capacitors? So currents passing through capacitors is a different thing as well, right? So for us to analyze currents passing through capacitors, let's see something here. A capacitor is always represented by two parallel plates with its end connected to a source. What happens is these ends are connected either to a DC or an AC. So now let's assume that it's connected to a DC here. Okay, so if it's connected to DC, then this is what happens. We have this here. So we have this here. The positive side here, negative side. So positive side will flow and it will stay at this ends of our capacitor. The negative side will also flow to this end of the capacitor. At the end, you realize that the charge from our voltage here will be stored across the capacitor. Then upon removing this here, when we remove this here, what happens is we can put a load being a bulb, right? Can put a load being a bulb here. Then finally, this charges will then flow back to light this bulb. That is the simple operation of a capacitor, right? So what happens is whenever there is a capacitor in a direct current, or in a DC circuit, what happens is the current can never cross it because apparently this side is an open circuit. It is an empty space which is occupied by air or any dielectric, which is not a conductor. Okay, so that is the reason why we don't use capacitors in our DC circuits. Capacitors will only act as charges or discharges in the DC circuit. Okay, unlike the AC, which occurs differently. Now, that was the explanation with respect to the capacitors. When you say inductor is something like this, a coil. Inductor is nothing. You can just create an inductor yourself, okay? So when you say an inductor is simply a coil of wire. So when you take a nail, or you can even use your own hand, coil the wires around it like this way, then you allow current to pass through this, okay? You allow current to pass through this. Now, what happens? You realize that this becomes a short circuit. Apparently, ideally, there is no resistance here, okay? But whenever there is an AC source, because AC keeps changing, in this coil, whenever there is a change in the electric field, from Faraday's law, there will be what? Induction, magnetic properties occurring here. So there will be a magnetic field to be created within this inductor. So inductors and capacitors are the key elements you are going to be doing in this AC circuit. Okay. So now let's proceed from our average value and the root mean value quickly. Okay. So let's talk about average value. Average value. Now, when you talk about average value in AC, as I said, because it keeps on changing its value, we need to represent it with a particular value for computation. So effectively, what is the source giving us? So this also called the DC value. Okay, so if you have an AC source, you say that the DC component, or if on average, if you are increasing from 0 to let's say 5 volts, then you decrease to negative 5 volts and come back to 0. On average, what is your effect? Okay, that is the whole goal of what the average value. It's like we are summing all the pieces of it and divide it by the total number. So we just want to get a particular or a specific value for it. So how do we find the DC value in any alternating circuit? To find the DC value, it's very simple. You need to first, number one, you identify your cycle. Okay, you identify a cycle within the circuit, because alternating current is a cycle. It has a sinusoidal nature. Number two, after identifying your cycle, what you do is you note the period. Note the period. When you talk about period, it is the time taken for the alternating current towards go one full cycle. So when it starts and when it's going to start again. Okay, so maybe you started from 0 and are starting at 6. You also go and start the next cycle at 12. So that becomes your period. So you keep on changing or going back to who you are at this particular time. That is period. Okay, time where an AC voltage or current starts and when it was starts again. That gives full cycle. So whenever you have this alternative circuit, you can just pick a single section of it which will represent the entire, because the rest will be a multiple of this. And the time taken for this to occur is what we call period. So after you've noted our period, the next thing you need to find is the area of the cycle you identify. Area of the cycle. This is very simple and very quick. Area of the cycle. So after finding the area of the cycle, finally we divide the area of the cycle it by the period. As simple as that. So this should give you the idea of average value or DC value. We have um, our, let's say, voltage, which is changing, okay, rising and falling at the same time. And now we want to find an average value for this. What happens? This, what you do is, instead of us summing each point, which we cannot do, what we are going to do is, we will first find the area. You find the whole area of this side, and let's say this side, assuming this is the whole cycle, right? So let me say I'm cutting the cycle out of this. So this whole is the cycle, have this cycle. Now once I have the cycle and I want to find my average value, I'll find the area. Now identify my cycle. After identifying my cycle, the next thing is I'll find my area of this cycle. Then what time did it take for it to achieve this cycle? Once I achieve that time, that is what we call the period. So once I get that time, I just divide it by my area and I get my average, as simple as possible. Now let's see how we can do this. So let's calculate this. So calculate the average. Calculate the average of a pulsating voltage. A pulsating voltage as shown below. So this is one of the simplest questions you will ever see in AC circuit, and I'm giving you a very simple waveform. So a waveform I have here, I have the voltage acting on the horizontal against time, right? So it starts at the peak, comes to zero, comes down, then move that way like this. So let's see how we can find the average of this circuit. Okay. So now if you have this, we have our peak to be E, we have the peak here to be negative E. So in this cycle, it goes past the zero, comes to the negative. Then from negative, it comes back to zero, then it moves to the peak in that order. So then from our stages here, we have identified a cycle. Now let's come here to identify a cycle. You realize that this wave started from this side, okay? Where does it start again? It's going to start from here. Is that not it? So you realize that we have a full cycle to be here and here. This is a full cycle, right? So once you have identified a cycle, this is done. The next thing is to note the period. So I have on my diagram, here is 2, this is 4, this is 6, we have 8, 10, and in that order. So for us to find our period is when it started and when it's starting again, okay? When it started and when it is starting again. So you can clearly see that it started from 0 here, and it came back to 0, came back to negative, and came back. So these are 4 cycle, right? So when you started from 0 here, and you are now starting again. And when am I starting again? I'm starting at 4, right? So if I have to find my period is simply going to give me this. So period is simply equal to 4 minus 0, and that is equal to 4 seconds, right? So now we have our period, we have our cycle. The next thing is to do what? Is to find the area of this cycle. What the area of this cycle? This is a square, okay? A square is a simple waveform. We have complex waveforms and simple. So since it's a simple waveform, we can easily find our area using the normal formula for finding area. So what is the area of a square? Now remember, this cycle is in 2 parts. It's a negative square and a positive square. So if I want to find the area, the simplest way you can do that is by labeling your cycle. I'll label this as my A, I'll label this as my B, right? So then what do? I find the area of A, and area of A is going to give me this is a square, right? So I won't say a square, but it's a square with, alright. But you realize that this, from the distance from here to here is E, and the distance from here to here is what, 2, right? So I'm going to have 2 times E, right? And that gives me 2E. Then I'll come here at the base here, I'll have still from here to here to be equal to 2, and the height then becomes negative E, right? So I'll have my area of B to be equal to 2 times negative E, and this gives me what? Negative 2E. So the total area then becomes what? 2E plus negative 2E, which gives me area to be equal to 0. Then once I have area to be 0, the next thing is to divide my area by on the period. So our average is simply equal to our area, which is 0, over the period, which is 4, that is 0. So meaning the average of this alternating voltage here is 0. Okay. So mostly, whenever they give you a sinusoidal wave and it has equal parts, with one part at the positive, the other part at the negative, obviously the area will cancel out and that will give you 0. Okay. So this is basically how we do it. Now let's quickly move to the second part, which we call the RMS value, root mean square value. So root mean square value, root mean square value. So this is also a nice thing for us to go through. Now when we talk about the root mean square value, it's also an effective value we use in AC circuits, and we mostly use root mean square value a lot. Okay, so how do we go by root mean square? Now the very first thing you have to do is to identify your cycle. First identify your cycle. Now once you identify your cycle all the time, the second point for you to do is to note the period of that cycle identified. Okay, you note the period. After noting the period in root mean square, since you have this square here, let this be a reminder. Okay, whenever you are doing root mean square, what you are supposed to do is you have to square the cycle. You have to square the cycle after you've identified the period. You square the cycle. And after squaring the cycle, you go and find the area of squared cycle. Area of squared cycle. Please pay attention to this because you find it in your in your final exams. They'll give you some waveforms for you to find the RMS, for you to find the average. So you find the area of the squared cycle. Then finally, you divide area of square cycle over your period. Then root mean square value. The last thing you're going to do is you take the square root of this whole expression. The square root of area over period. Okay, square root of area over period, and this finally gives us the RMS value. So let's quickly get this simple question as well. So I'm giving you this waveform here. If I'm to give you this waveform, I have this here. So calculate the RMS of this waveform. I have this here. Then it starts like this, like this, like this. So I have this peak to be negative E. I have this to be positive E, right? Now I have 2, I have 4, I have 6, I have 8. What do I do? I'm to find the RMS of this waveform. To find the RMS, first of all, identify your cycle. What is my cycle? Cycle, as I said, is where the AC parameter is starting and when it's going to start again. So obviously, it's going to start from 0, right? So start from 0, come down to 0, then it's also starting from this side here, like this. So this becomes our cycle. Once you identify our cycle, we need to note our period. To note our period, where does it start? Here is 0, right? So we have 0 at our starting point. Then we are going to have here, which is 4 as our ending point. So period is equal to 4 minus 0, which is equal to 4 seconds, right? The next thing is to square the cycle. When you square the cycle, what happens? This side will what? Go up, right? It will also become positive. That is what you should take note. So we are going to apparently have a new waveform where we have all of them moving up because the negative ones will also fill up and you get our E squared here, meaning that this will move up, this will move up. So to switch up like this, to switch up like this, right? So now we have here, you know that 0, 2, 4, 6, 8. So we find the area of the squared cycle. So with the area of this square cycle, how do we do it? We say that A is equal to what? We have our length, then we have what? Our breadth, right? So area of this square cycle, we're going to have, you remember that this was the identified cycle, right? So since you squared it, this will add it to it. Now we can see that our cycle is now looking this way. Our cycle is now looking this way. So we have this to be our cycle, which is two different shapes, I can still label it as A and B. So for A, I'm going to have 2 times, so it's E squared, right? Then B is also equal to 4 minus 2 times E squared. This gives me 2E squared. This also gives me 2E squared. Therefore, I'll say that the area of my square cycle becomes what? My total area becomes 2E squared plus 2E squared, right? This gives me 4E squared, and this is the entire area of our square cycle. Then we divide this area of the square cycle by the period, which is 4. So 4E squared over 4, this gives us what? E squared. Then finally, we take the square root of what this expression, that gives us, this cancel this, we get E, right? So E is now our RMS value for this entire waveform. So next, let's solve actual question here and see how we can apply this, right? So I have this question here, so beautiful. Now I hope you are familiar with this question. So let's apply the knowledge we had here once again. Okay, okay, so I have these two questions. Number one says calculate the RMS value of the voltage waveform below. Then number two says consider the waveform below. Then we find the average value. We determine the effective value of the waveform. Okay. So to tackle this problem here, what do we do? Now, number one, so I have this waveform here. You follow the process. Now we are dealing with RMS. Okay, we are dealing with RMS. But before then, let's go through one thing. From this side, we realize that I gave you shapes which were all regular, right? So I gave you regular shapes. Now, looking at this, okay, looking at this, there is possibility that you be given shapes which are not regular. So if you have such situation, what happens is you are supposed to use integration to simplify the area of the square cycle. So now let's see how we do that. So simply, when you say area, we know that area in integration or integral, you say that area is the sum. So I have, let's say, this diagram here. I have this shape, let's say this shape here or something, right? Then 0 to, let's say, x. This value here is, let's say, e. Now, if I want to find the area of this entire shape or entire graph, I need to know the function of this, and that will be f of x, right? Then the next thing is this is my limit of integration. I'm trying to sum up all these points small across 0 to x. So we take integral from 0 to x and a function of f of x dx. So this is simply the area of any function provided that you cannot use the basic formulas to find. Okay, so you simply have to find the function of that particular cycle, then you take integral from one end to the other. Now in the case of the um, RMS, which the root mean square value, it says that you square your cycle. So the cycle identifier is your function f of x. When you square, you are going to get f of x all squared, right? Then the next thing is to take integral 0 to x of f of x all squared. This becomes the area under the square cycle. You divide this by your period. So 1 over t, you divide it. Then finally, you take square root of everything. Now, this whole expression here is mathematically root mean square value of any square, any waveform, okay? Any waveform. Just identify the function here, okay? So now let's apply similar thing to this. Now, let's take the first one. I have this here. I have this. I have this, right? Like I said, I have. You can see from this side, right? So I have this whole. I have this waveform here. I'm to find the RMS of this value. Now, whenever you are dealing with triangles, please take care. You don't find the area of triangles as we know half base times height. Okay, you don't really use that here. So please watch closely as I show you how to find the area of any triangular waveform. Given any triangular waveform, please divide it into two like this, right? So that you get in. So I mean, I'm going to divide it into two like this. So this is 90. So you're going to get two separate right angle triangle from this. Now, let's take right angle triangle. The reason we are taking this is if you have a Cartesian plane and you have a line in space, this is simply the equation of a line. I'll simply draw this dashes and this forms a complete right angle triangle. I can find the area under this line and that is simply what you're going to do. Okay, so you're going to find the area under this line, which we consider it to be what? Half or right angle triangle. So this is going to have two of this. So have this part and this part. Okay, so let's see how we can use integration to solve our questions here. So first of all, to find the RMS value, you identify the cycle. What's the cycle? The cycle starts from this and starts again here. So the cycle is simply from here to here, then we come here. This is the cycle. We move from here to here, then we come here, right? So this is the nature of the cycle. From here to here, then we come here. But currently here is zero, so you will not consider it in the area. Okay, we focus on this side. But for the period, it will be taken into consideration. So we have identified our cycle. The next is to identify our period. Our period T is simply equal to what? We are starting from 0, then we move towards 6. So it's going to be 6 minus 0, and this is equal to 6 seconds. We put that down. Now let's come to our half triangle. With our half triangle, I'm going to have the base below 2 minus 0, which is 2. Okay, and the height is what? 3. But we are not going to find the area that way. So watch closely. Taking one right angle triangle, this is what you do. Generally, we know that integral from 0 to 2, right? Then the function, which is f of t, dt, gives me what? The area under the cycle. So if I want to find the area of the squared cycle here, now if I want to square the cycle, that becomes a challenge. Assuming that you want to find the area of the squared cycle here, we use integration to do that, okay? So for us to use integration, as I said, let the function be a function of time. So a function f of t dt. So we are integrating from 0 to 2, then f of t all squared because area under the squared cycle dt. Okay, so this is exactly what you're going to do. But now, what is the function? If you take any right angle triangle, what will be the function? As I illustrate that to you, I have my right angle triangle here. Now, we assume that this is a line in our Cartesian plane. Okay, this is the line, and we are trying to find the gradient. So generally, know that y is equal to mx plus c, right? Then since our line is touching here, we are going to say that c is 0, right? C is equal to 0. So we're going to have y is equal to mx. Now we say that y from the question is v, our v, right? Or our v, we can equally see it, right? So we can say that our v is not equal to m is our gradient. What is gradient? Change in y over change in x. Change in y is what? 3 minus 0 over change in x, which is what? 2 minus 0, right? 2 minus 0. So we get 2 over 2 times what? Our x here. And now x now here is what? Time t. So we simply represent our x here with what? Time. So now this is done, but I'm not done. I'm to find the same for what? The right angle triangle. But we've already gone through that. Okay, so we can say that the right angle triangle is going to give us h squared b over 3, where h squared b is the same as well. So I'll have vm squared pi over 2, then the h I'll have plus. This becomes, my h is what? Vm. So I still have vm squared. My b is what? My b is from here to here is pi over 3. We have gone through in the previous question, so you can solve that where I gave you the expression. Or well, we can still go through again. Let me take you through once more. So for me to take you through, let me just clean this part and let's solve for the area under the right angle triangle once again, in case anybody missed that also, and for this particular question. So to solve this, um let's see. Yeah, right. So this is how it goes. So area under right angle triangle, like this. So what happens? As I told you, you need your function. So we need a function v of theta. Now it's theta. How do we get it? This, we consider it to be a straight line in our Cartesian plane, which we are finding the area across. So we need to get a gradient. So it's the same as y is equal to mx plus c. But here c is 0 because it's passing through, we assume that it's passing through the origin, right? So it's touching y at 0, right? So we're going to have c to be 0. We eliminate c. Once you eliminate c, you're going to have y is equal to mx, where our y is now v is equal to, the gradient is now what? Our y on x, and our y is of vm, and our x is of theta. Okay, so v of theta is now equal to this. The next thing is to square this function. When I square this, like, I'll have vm squared over theta squared, right? So now this is my function which I'm going to what? Integrate. Okay, this is the function which I am going to integrate. So sorry, oh no, I've made a mistake here, so sorry. So I want to find a gradient. Gradient is actually the change in y over change in x. Change in x is 2 pi minus pi, so it's actually pi. Okay, pi. So vm squared over pi, then I add my x. The x is now what? Theta, like this. So integral from 0 to, now we are not doing from 0 to pi, but it's rather from what? 2 pi to pi is the same as 0 to pi. Okay, so we say that from 2 pi, from pi to 2 pi, and our function is now vm squared theta over, here pi is simply what? A constant comes out, then once pi comes out theta. So area under the square cycle become vm squared over pi squared times theta cube on 3, right? From pi to 2 pi, right? So when I put 2 pi, I'm going to get, I mean, doing from pi to 2 pi, you can simply make it 0 to pi. Okay, for simplicity, it's the same thing. So it's the same pi interval, so 0 to pi. So when I put 0, everything will be 0. When I put pi, I simply have vm squared over pi squared times pi cube over 3, right? Pi squared cancels off 1, goes here, pi. So simply we get vm squared pi on 3. And that gives us what? Vm squared as our h height. So always, for every right angle triangle, the area under the square cycle is given as h squared times b all over 3. And this is how we got that. So we simply have this. We sum up the area under our square cycle. So what do we get? We use, I have vm squared pi over 2 plus vm squared pi over 3. So when I add this, I simply get 3 times this, which is 3 vm squared pi plus 2 vm squared pi all over 2 times this is 6, right? It's 6. But yes, it's 6. So we're going to have this here. Um, so this gives me 5 vm squared pi over 6 as the total area. Then we come to divide this by our
period. The period for this entire function is from 0 to 2 pi. Okay, so it's 2 pi. So I'll divide this by 2 pi. And this now becomes 5 out of 12 Vm squared pi. Okay, like this. So 5 out of 12 Vm squared pi is what we've got. Then the next thing we're going to do here, I'm sorry, when I divided by 2 pi, I have to cancel this pi away. So I'll simply get rid of this pi. Okay. So I think my working space is messy, pardon me. And I'm going to have 5 out of 12 Vm squared. Then I'll take square root of this expression. Okay, I simply get Vm square root of 5 on 12. And that gives us our root mean square value of this waveform. I hope you got it, and I believe that you understand all that we are doing, right? So we still move on. And this is all about root mean squared, average. I think we've solved enough questions. So at this point, we can proceed to some one or two conceptual stuff. So now let's see. So sinusoidal voltage and current. What's the whole concept of sinusoidal voltage and current? Now we're going through this simple. Okay. So now let's see something here. Because voltage and current appears to follow the sinusoidal wave like this, we tend to give a functional voltage and a functional current for every AC voltage or like alternating voltage, alternating current. Okay, so this is what happens. Normally, we know that V is the voltage across any conductor. In the case of AC, we say that our voltage is equal to the peak voltage achieved in our sinusoidal or in our cycle sine omega t. Okay, sine omega t. You can also get Vm sine theta in some situation, or V is equal to, omega is equal to 2 pi f, right? This angular frequency. So Vm sine 2 pi ft. Put this in your mind. Then the next thing is I, current. Current is also Im sine omega t. Okay. Now, the truth is, in sinusoidal current and voltages, current and voltage are always not in phase, unlike the voltage and DC. Okay. So I'll prove that to you in calculation with capacitors and inductors. Okay. Capacitors and inductors. But for now, let's go strictly by this. So from here, let's solve this question here. So find the frequency. Find the frequency and RMS values of the following quantities. So I'm giving you alternating quantities. I have the first one A giving us I is equal to 10 root 2 sine 100 pi t. I have B, V is equal to 100 sine 120 pi t. We have to find the frequency and the RMS value for these quantities. Now, generally, I skip this. If you have your peak voltage Vm, then let me write peak voltage. Then the RMS value, okay, is always equal to your peak voltage over square root of 2. Please take note of this. Peak voltage over square root of 2. Vm peak voltage is equal to Vm over square root of 2. Then the average is always equal to Vm over pi. Okay, so these are sinusoidal waves parameters. So far as it's following the sinusoidal wave, well, if unless maybe it's a square wave, that is when it differs. For every sinusoidal wave, these are the parameters you should take. So this can be current IM. We can have IM over square root of 2 as the RMS average. So always, whenever you are dealing with sinusoidal wave and if it tell you to find RMS, don't go through the process. Just write your parameter, that is your peak voltage or current over square root of 2. To solve this problem, we need frequency, we need RMS value. What do we do? You have to express this in the standard form. I and you know that current in alternating circuits is equal to peak current sine omega t, which is equal to peak current sine 2 pi ft. We compare this to this. That's what we do. So 10 root 2 sine 100 pi t. When I compare, I have 100 pi t. When I compare, t is here, right? I have t, I have t. I have pi, I have pi. What do we see? We can easily see that after the sine, I have 2f, I have 100 pi. So you simply have to equate them, okay? So first of all, I can say that before the sine, I have Im, before the sine, I have 10 root 2. So therefore, my Im peak current is equal to 10 root 2, okay? My RMS then becomes Im over square root of 2. So I'll have 10 root 2 over square root of 2. And my root mean squared simply becomes 10. The next thing is to find the frequency. How do you find the frequency? Sine of this expression. So the expression coming after the sine, I have 2 pi ft should be equal to 100 pi t. T cancels t, right? Pi cancel pi. I have 2f is equal to 100. Obviously, f is equal to 50 hertz. That is how we solve it. Okay. Now, the next thing is to do the same for our voltage. Obviously, we can use our eyes to say that we have 100 to be what our peak voltage, right? So if you want to find the RMS voltage, it becomes the peak over square root of 2. So therefore, we simply going to have this here. We're going to have our V to be equal to 100 over square root of 2. And that is equal to 100 over square root of 2. That is 70.7 or 50 root 2. 70.7 volts. Then the next thing is we should find our frequency. So as I said, equate all this time towards the this time. So 2 pi ft should be equal to 120 pi t. T goes with t, f will be left, pi will go with pi. So I have 2f to be equal to 120. 2 goes here. So our frequency is 60 hertz. 60 hertz. Basically, this sinusoidal wave and voltage. Now, finally, let's go through harmonics. Then we end for this section of our AC. We will continue with power and other stuffs in our subsequent tutorials. So harmonics. When we talk about harmonics, okay, harmonics is it's a term used in frequency, pitch, sound is something we use, right? So what does harmonics go to do this? Always we have what we call the fundamental frequency. Fundamental frequency, okay, represented as F naught. Multiples of this frequency is what we call harmonics. I can have twice F naught, 3 F naught, 4 F naught, okay. So we call this harmonics. So we have the we can have odd harmonics, we can have even harmonics, okay. What's the essence of this? Sometimes a sinusoidal wave will be represented as harmonic, that is, of different frequencies. Whenever you are handling such waveforms, you need to be very careful. You cannot combine a frequency of 2 F naught to 3 F naught. It's impossible, okay? Take notes. Whenever they give you two different waveforms where we have two F naughts or a frequency of two F naughts, another frequency of three F naughts, you cannot combine them. They always remain as they are. Now, how do you find the root mean squared of all harmonic value? Okay, so a typical one is a function of t is given as, I'm giving a typical example of a harmonic. A naught, A1 sine omega t plus our angle 1, right? Plus A2 sine 2 omega t plus our angle 2 plus A3 sine 3 omega t plus angle 3, right? Like that. So you can see that here we have a frequency of omega t. Here we have a frequency of 2 omega t. This side we have a frequency of 3 omega t. So we cannot combine them. To find the root mean square of this situation, what we do is we simply take, this is a linear, okay. Whenever you don't have any sign attached, it means this is an AC component, okay. Now the AC component is treated directly, so we say A naught squared. Now this is the DC component, okay. So the AC with the sign, we treat it as we know. I'll identify my peak voltage, which is A1. I'll divide it by square root of 2 to get my RMS for this particular harmonic. Then I'll square. I'll come to this. I'll have A2 over square root the RMS squared in that order. Okay. That is how we do this. Okay. As simple as that. Now, let's take this question. So find RMS of I of t, which is equal to 2 plus 5 sine omega t plus 3 root 2 sine 3 omega t plus 30 degrees. So how do we do this? This is omega t, 3 omega t. We cannot combine them. We call them harmonics. We treat them independently of each other. We'll get to a section where we add in different waveforms. So here, to find my RMS, I simply open my bigger square root. This is a DC component. I take 2 squared. I identify my peak voltage in this AC waveform. Here I have 5 over my square root of 2 all squared plus here I have my 3 root 2 over root 2 all squared. And finally, I put my answer, and my answer is simply going to give me 5.05 amperes. So these are some of the basic things you should know as you are doing alternating circuit. Okay, so with alternating circuits, you only look out for RMS average. You should be conversant on how to identify cycles and all that, and have control of you. So from here you move to phases. Okay, we move to phases, and or we say phasor diagram, how to represent, then move to impedance. So I would like to end here with this part. The next time will be um, in-person tutorial. So with that one, you'll meet in person. So time and venue, everything will be communicated to you appropriately. Thank you for joining this, and I hope to meet you in our subsequent tutorials.